s'agit du dernier séminaire de l'année académique, avant la coupure estivale. Nous avons aujourd'hui le plaisir de recevoir Canizo, qui nous vient de l'Université de Grenade, qui passe un petit peu de temps en France. Encore une semaine, hein, tu m'as dit?
Oui, encore une semaine, après je reviens.
D'accord.
Donc, c'est un total de presque un mois.
Un total de presque un mois. Venu ici au laboratoire et nous allons avoir le plaisir de t'écouter sur le sujet suivant. Donc, il s'agit d'approximation non locale de Fokker-Planck. Quoi.
Merci bien. Donc, je remercie l'organisateur du séminaire, aussi Maïman qui m'invite à passer presque un mois ici, de mathématiques au ONS. C'est toujours un plaisir. So, I switch to English and I will explain a bit what I want to talk about. So it's about the local problem that it's an ongoing thing that we are working on. So I want to explain to you more the technique. I think it's an interesting result, but to me the most interesting is the technique to arrive to this kind of result. And in collaboration with Joe Evans, Alejandro Garri, and Niccolo Tassi, who is now a student at the University of Granada. And what I will do is I will show you directly the equation, and I will give you some motivation and some reasons why we are interested in studying this kind of thing. Okay. So the equation is really easy. In more than one sense, you will see it's a linear equation, and it contains two parts. So the unknown is this u of tx, depends on time, and it depends on the position x. X is a space. The equation, as I said, and it has two terms. So this first term here, this divergence, it's a potential. Okay, some kind of confinement potential. As usual, it's x squared over 2, which is, if you think of this as density of a particle, it's making the particle go back to the origin. And the part on the left, it's a non-local operator. It has a smooth kernel, and the effect is that the particle has always some chance of jumping a certain distance, and the distribution of the distance a particle can jump is given by J. So this kernel J will look always like this. Okay, so this is 0. It will always be something like this, and it's compactly supported. It's smooth, and if you want, it's symmetric. It has so the problem is not the singularity of the kernel. Okay, rather the problem could be more the fact that it's not singular at all. So these are the properties that we set on the kernel. So we always consider that it has integral 1, so that the equation above, it preserves mass. Okay, so the integral 1, it's so that when you integrate both terms of the equation, you get 0 formally. Okay, you get 0 from the divergence, and then the convolution will give 1, and it compensates exactly with the minus u. So this is mass conservation. This is to make sure that we have the right approximation to this equation below that I will mention in a moment. And we normalize the second moments for the reason that I'm going to explain now. So that one of the interests of this equation is that there's a rescaling going on here in epsilon. So this J is the jump distribution, and we rescale it when epsilon goes to 0. So that J is approximating a delta. So what's happening is that the size of the jumps is getting smaller, but the intensity of the jumps, which is given by this 1 over epsilon square, is getting larger. It's the same kind of rescaling you would do if you want to go from the usual random walk to a diffusion. Okay, the same kind of scaling you would do. So when epsilon goes to 0, this equation looks like this one here. This is quite well known, I would say. Anyway, it's very easy to do this. So I would just want to do a very short formal proof of this. So this operator here, okay, that we have, it's the epsilon u minus u. This thing here is exactly this. Okay, so if we evaluate this in x, we will have this. Let's say we do it in r. Okay, so we have just the epsilon of x minus y, and then I can do this trick, which is write u of y minus u of x dy. The reason for this is that the integral of j is 1. Okay, so in this term I put it artificially there. So what is this then? This is equal to the integral of epsilon minus 1 j of x over epsilon, okay, minus y over epsilon, like this. I'll have the same thing, dy. And now I do the change. Z is going to be x minus y over epsilon. So that gives me that y is going to be x minus epsilon z. So I get this. I get as it's written here. So I get as it's written. So in the differential, I put inside the 1 over epsilon. Okay, so this will give me j of z u of z minus ux dz. Okay, so now what do? You expand this in Taylor series. What's happening here? The first term is cancelled exactly by this one here. The second term disappears when I integrate, because I have the condition that x times j is 0. The last term has a given coefficient, which is the one that I wrote there, which is 2. It has a 1/2 from the Taylor, so it gets to 1. And since there's an epsilon here, the second term, which is the first remaining, has coefficient epsilon squared. And that's why we have epsilon squared there. Okay. If you do this in higher dimensions, it's the same. You just have to take care that here you will get all possible second derivatives with the Hessian, right? So that's where the 2D comes from. So this convergence is quite well known, and it's very interesting. And in this particular case, depending on what you're interested on, you could study it by Fourier. So one observation, which is very important, is that this equation is kind of a toy problem. I could solve it by Fourier, but still, the things I'm going to prove, I don't know how to show them by Fourier. So what's the kind of things I want to show about this equation and this convergence? Okay, what are the kind of questions that I would like to study? So since it's an approximation to Fokker-Planck, it's very natural to wonder whether it will have the same kind of asymptotic behavior as Fokker-Planck has. Does it have a unique equilibrium? The answer is yes. Okay. How does this equilibrium behave? This is non-trivial, especially for the tails of the equilibrium. Even for this very easy problem, this is non-trivial. Now, can we show that we approach this equilibrium uniformly as epsilon goes to 0? So Fokker-Planck is an equation that has a spectral gap. It approaches the equilibrium at a given exponential rate. Is it true that the exponential rates of approach to equilibrium for this equation converges to that of Fokker-Planck? Or at least, is it bounded below by some constant where I can show? So it would be, if I prove this for this equation, I prove the convergence, it would be like an alternative proof that the Fokker-Planck equation goes exponentially to equilibrium. Okay, so this is the kind of thing that I'm interested in. This kind of thing, I will mention it further later, but has to do with some recent results on numerical methods. For some numerical methods, it's very interesting to know whether you have an asymptotic preserving method, meaning that, okay, you have a good approximation on a compact time interval. Is it true that you have, can you design a numerical method that has a good approximation for all times? Okay, does it have an equilibrium which is the same or close to your limiting equilibrium, and does it approach the equilibrium in the same way? So there could be the simplest numerical method for, I don't know, the heat equation. Maybe if you don't do it carefully, it doesn't conserve mass, or it doesn't decrease energy. So weird thing can happen. So it's an interesting thing. I mentioned here some results on this, which are really on this topic. So there's a book, okay? This Andreu Mazón is called non-local diffusion problem. So we understand this non-local term as some kind of non-local diffusion, even if the kernel is regular. And they use all the techniques, compactness techniques, all the things, but they do a lot on the Fourier transform. Okay, so for this problem in particular, it's quite well studied on the Fourier transform in that book. Then this paper, it comes from the point of view of kinetic equations, but also from the point of view of numerics. And what they do here is to study this equation and the similar equation without the divergence, and look at the convergence of equilibrium in these Fourier distances that have been used a lot for kinetic equations, for Boltzmann models with Maxwellian interactions. Okay, so it's something that Toscani has a lot on. There's a good account of this in a review by Carrillo and Toscani. Okay, so these kind of distances, Fourier-based distances, they are very useful for this, and they work very well for this kind of problem. And then I learned also that there's a result by Michel Trisani, where they study exactly this kind of convergence. Okay, so the result I'm going to give later, it's essentially stated there, and the technique is different. So the main innovation, the thing I want to tell you about is the technique to do. So I have several slides on motivation. Okay, so I know that there are several people who are experts on this in the room, but I will go through some motivation for those of you who are not so familiar with this. And this is a model. No? This is one of the reasons we were interested in this model. So this is a real model people have proposed in papers in physical review, in papers in biology, for the expression of a gene. So this U, it represents the probability that a certain protein has a certain concentration. Okay, so U is a probability, and the integral of U is conserved. So what's happening is that you have some genetic information that's producing a protein, and the production of the protein happens what they call in bursts. So for some reason, there's some biological process that switches it on, then you produce a lot of protein, and then you stop. And there are some experimental results. For example, there are experiments where you see that either you see some concentration of protein low, or you see some concentration of protein high, and you don't really see the ones in the middle. So that comes down to saying that the equilibria for this might have two maxima, right? Or maybe they only have one maxima. So it's an interesting biological problem, but it's very simple. It's linear. So this person, Pájaro, was working with other people on this. And then we tried to study, and we thought, okay, this is a very simple equation. It contains the same drift term as before. Okay, this equation is posed on 0 infinity. I haven't written it, but this is on 0 infinity. So these are the bursts. So what's happening to the protein? It's degrading. It's degrading as time passes. So if you have X amount of protein, each one of them can independently degrade. So the rate at which it goes down in the appropriate limit is just times X. Okay? It's like polymers. The instantaneous probability that polymer size 10 degrades is 10 times the probability that one degrades. Okay? This is why you get the X cubed there. Then this one, it's one-sided. It's like the J we have, but it's one-sided. If you have this burst, it's a production of protein, and it makes the concentration of protein jump to a higher point. And this C is a modulation which is bounded above and below, and it's important for the biological model. Okay, I don't fully understand the biological derivation of this, but they have explicit expressions and experimental constants and everything. So the difficulty for this is that this equation here, I cannot do a Fourier transform because this C has a weird form. It's not exactly a full integral. Okay, it has some technical difficulties, especially the C. So we did study this in this paper from some time ago, and we did it a bit by hand. So this equation has an entropy. You can write the entropy dissipation. You can try to prove an inequality, and we did this by hand somehow. Okay, it's an inequality. You study it. And the same as you can do for other equation, it's a functional inequality. That's interesting, but you can do it, right? So there's a natural question of for which equations like this you can do this kind of thing. This is the question I want to get to. There's another motivation here. Another motivation for which maybe the technique I'm going to tell you doesn't work is the Boltzmann equation. If you consider the linear Boltzmann equation, meaning you have particles interacting with a background, the background is fixed. You have collisions with the background, but the equation becomes linear because there are no self-collisions. Okay, the equation looks like this. Okay, there's a kernel which is not j of x minus y like here, but it's still a kernel, and it's complicated. Okay, but it's explicit, and you can bound it. So the one I've written here is the simplest one, where it's a cutoff version. This gamma has to do with whether the potential is hard or not. Okay. But it's explicit. You could wonder the same. You could say, is it true that I can study the convergence to equilibrium for this using the usual techniques, entropy, probabilistic techniques, these kind of things? So this is done. This paper, I would say, it is essentially Fourier-based, right? So you start with the case of Maxwellian molecules where you have an explicit solution. You can solve it by the Fourier transform. Once you do that, you can compare this equation to the Maxwellian case, and then it works out. Okay, so it's good. Then here, with Maxiavisi and Bertrand, we wanted to do this, but for the entropy. So if you want to study the logarithmic entropy, like the Boltzmann entropy, then you get an inequality, which is kind of horrible. And then we played around with it and everything, and there's a kind of a surprising inequality, which looks a bit like a Blackman-Stam inequality, but for the Boltzmann operator, which was done by Villani. If you use this inequality, it fits amazingly well with the Boltzmann equation. Okay, it doesn't fit with anything else. So I tried because I said this must be a great idea. It is a great idea, but then can you use it for something else? I don't know to this day. So it would be nice to be able to do it for a much simpler one like the one before, right? But I don't know how to do it. Okay, so it works for this one. So it works for the complicated one. But I don't know how to do it for the simple one. And then the last motivation, which is maybe a bit further away, but it's the same kind of idea, is that in many numerical methods, so a numerical method is a non-local version of a local equation. Okay, it becomes non-local in the sense that you have to use 2 points which are close to one another and something. So if you keep that in mind, then letting the discretization go to 0, so the discretization parameter go to 0, it's approximating a local equation by a non-local equation. And there are lots of recent works on whether these schemes are asymptotically preserving. Are these schemes asymptotically preserving? Here are some references. Okay, so this one here is not far from the kind of results that I'm considering, but it's for the fractional Laplacian. Okay, so it's a numerical method for the fractional Laplacian. And these people here, so there are several papers, and I don't know all of them, but they have this plan, I would say, to study asymptotic preserving methods in a rigorous way, proving that your method approximates the limiting equation. Okay, so this is an idea for the motivation. So let me give you just a short overview of what you could use to study this kind of equation. Okay. So how do I know that the Fokker-Planck equation, which is the easiest one here, converges to equilibrium? This is a standard method. This is what I would call an entropy method, and it's being used a lot for this kind of equations, also in kinetic theory. Okay, it works like this. I invent this kind of entropy, which is very general for linear equations, linear positive mass preserving. You can always find it. I get this dissipation, and this is an inequality, which is called a Poincare inequality with a weight. You can prove it. Okay, so no, there's a book on these kind of things by Bakri, Gentil, and Ledoux, and it's a good place to look at this. But this constant is a good one. You get this, and now to use the Gromwald inequality, I know that ddt of this is less than -2 of this, so I obtain this immediately. This here, it's a weighted L2 distance. So this means this equation has a spectral gap in this norm. Okay, it's a way to let's say it's a definition. Okay, I say it has a spectral gap in a certain norm if I can prove this kind of inequality, maybe with a C here. So this is easy. Can I do the same for the approximating equation? The approximate equation, it's almost this one. Okay, it's almost the same. Can I do that? Okay, no, I have another slide on the logarithmic entropy. Okay, if I do it for the logarithmic entropy, it's not the Poincare inequality, but it's the logarithmic Sobolev inequality, and this is exactly the good constant. So this is the famous logarithmic inequality, logarithmic Sobolev inequality by Gross, or maybe it was written even before by other people, but that's the famous reference. And you get the same. Okay, you get the same kind of decay in relative entropy. So this is what it's called the relative entropy between U and G, and you see it decays. So in particular, from this, you can know that it decays in norm L1. It's easy to see that the norm L1 is bounded by the square root of the entropy. Okay, so what about the local equation? The non-local equation. If I try to do the same for the non-local equation, then this is still true. Okay, and this is a Markov process, and the fact that there are entropies for this it's old, I would say. But so this paper where it's done for many models in a large family of models in biology, in probability, and it's also for non-conservative equations, right? So even if the equation is not conservative, you can do some kind of rescaling of the equation and still apply the same kind of method. But this one is really the classical case. This equation, it's the evolution of the law of Markov process. So I have this, I can calculate this here. And now the question would be, is it true that this quantity here with a plus is larger than the entropy here? Okay. This inequality is not super easy to prove. There's maybe some ideas to do this. We did something like this in this paper with Carrillo and Pájaro. Okay. But well, I cannot give you a reference where it said under these conditions this inequality holds. I don't know it. And also, it would be interesting to say that there should be an inequality stable as epsilon goes to 0. I would like to say that the constant inequality stays the same or converges to something as epsilon goes to 0. So it's a limit from some kind of non-local inequality to a local inequality, which is Poincare. So this is also not clear. Okay, this is interesting, but it's also not what I'm going to explain. There are other things you could do, which I would call maybe operator methods, and they are somehow heritage of the perturbation methods by Cato. So it's where you they can be made quantitative, they can be applied to particular problems, but the idea is that if my operators, as an operator in some Banach space, converges to the limiting operator, then maybe the semi-group also converges. And there are ways to do this, and there are lots of papers on this. I just mentioned some of them. You can see the references. So this is where there's a general presentation of this kind of technique. And so this is the paper I mentioned before, where this problem is studied by these arguments. And there are several applications to biological models, either neuron type models for the behavior of a population of neurons, or for the behavior of a population of cells, where you have growth fragmentation type equations. Okay, so there are lots of results on this. So what is the tool then I want to use to tell you how to say something about this equation? So it's called the Harris theorem, and it comes from probability. And I think it's very useful in many PDE, and still it hasn't been used to its full potential, I think. So this is one example. With this method, with the estimates that we have been trying to do in order to apply this method, we're able to prove some positivity estimate for this kind of non-local diffusion equation. So this is hard to do by Fourier, because positivity doesn't play very well with Fourier. So let me explain a bit about this theorem, and then I tell you how to apply it for the non-local equation. So this theorem is called the Harris theorem. And in order to apply it for a Markov semigroup, so you have something, you need to have some evolution which is linear. It has to be positivity preserving, and it has to be mass preserving. Now it has to satisfy two things. I say there's some space. I have some. I think it's better if I write here. Let's say this is my state space, and I have some macro process where a particle it's moving around randomly. Okay, and the evolution of the probability is the PD I'm looking at. So let's say I decide this part of the space. I will call it the center of the space. Okay, I give it a name. I say this is the center. I need to prove two things. One, if I start with the particle not too far from the center, at some point it will get there. Okay, this is the thing. So at some point it will have a uniform probability, a uniformly bounded below probability of being here. So there's the total probability of being in this center has to be bounded by some positive number. Okay, this is the first thing. The second thing is if I start very far away, I need some kind of confinement property. So the typical kind of confinement property that you prove for the most usual equations is some moment bound. So I prove that some moment which controls the amount of mass, the probability of the particle being far away, it's uniformly bounded in time. And I have to prove some inequality like this one here. Okay, something else. Okay. So you prove something like this. So this is the moment of order k. If you're able to prove that it's bounded by some kind of inequality like this, so the gamma has to be negative, okay? It has to be strictly positive. Then you say these two things. If you start too far away, then you cannot escape because the moments are bounded. Once you are here, all particles at some point they have to be here, and this gives you a contractivity. So in probability, they call this a coupling argument, and it's a really nice idea. And let's say if you have a bounded state space and you can do this from everywhere, then you don't need the other condition, right? If you can prove that you are positive everywhere, if you start anywhere, then you already have a proof of the convergence to equilibrium, which is really, really fast and very nice. So I want to give you some more precise statements. The conclusion, if you're able to prove these two conditions, is that you have exponential convergence to this unique probability equilibrium F in this weighted norm. So it's L1 with the weight K. And K is the one where you have studied the moments. Okay, you will get some kind of exponential convergence. You see that there's a C here. This C will be larger than 1 in general. The smallest it can be is 1 because at t equals 0, it has to be 1. So you get exponential decay to equilibrium. So at time t, it's much smaller than it was at time 0. Okay, so depending on this C, and you get a good estimate on this constant. So usually this estimate is not optimal in any way, but it's a uniform estimate. So this is a more precise statement. Okay, this more precise statement gives you a bit of more general conditions under which this can hold. So you don't need, for example, the strict time decaying inequality that I wrote before for the moments. It's enough to know that at a certain time t, a given moment will be smaller than at the beginning, except for a multiple of the mass. Okay, this is fine. So this is the Lyapunov condition, and the Harris condition is this. So this nu corresponds to this thing I call the center of the space, and so you have to know that if you don't start very far away, okay, so meaning that your initial probability is supported not too far away, then at time t it's uniformly positive times this fixed probability nu. So if you know that your equation is uniformly positive with a uniform bound for all initial conditions, if you don't start too far away from the point of view of the PDE, and you know that the moments are bounded by an inequality like this, then you can prove exponential convergence in this weighted L1 space. So we'll give you some references for this, and there are lots of them. So there's all data by Harris, but I don't think this theorem is proved here. In general, it's attributed to Main and Tweedy, so there are books on this, on the convergence to equilibrium for macro processes, and this is mentioned there. Then there's this proof, which is really nice, and it's really it's a proof based on probabilistic arguments, but it's much closer to a PDE argument than the coupling proofs. And it's very nice. It's based on transport distances. And then recently with Mishra, so it appeared this year, but we have been working on it for at least 2-3 years. We gave a simple proof. Okay, so the proof of this theorem, it's really elementary and doesn't need anything like a process or anything like this. I just need a semigroup which preserves mass, positivity, and is linear. That's the only thing. I don't even care about the regularity of the thing. Okay, so it's really it's very elementary. I will show you in a minute. And there are all the papers where there are generalizations, there are applications to particular equations, and there have been others. Okay, so there are a few people here that have been working on this, like on applications of this to several models. I have been doing this. Habayoldas, who was my student, Delphine Salot, Ambrogi, Stéphane C. So yeah, there are a few people that have been working on this, and so it has some application to interesting models. And I want to give you a very elementary proof. Okay, it just misses one step, which I will tell you now, but it's really not very. It's really elementary. So the thing is the following. So this is the really L1 norm of the difference. So I want to study the difference to equilibrium. What I do is I discretize the time. Okay, I do jumps of size t in time. I want to prove that this Wn goes to 0 in some norm. So this is the W1 norm, and this is the weighted norm with the moments that I can study. So there are these two things. If this is always true, okay, this is the decrease of the moment that I was mentioning. Okay, so the moment at time the next time is less than the moment at the previous time plus some multiple of the mass. Okay, so I can prove this with the conditions before. Now this one, it tells you if you don't start very far away from the center, then the mass, the distance in L1 will decrease. So this means that this moment is not too large compared to the L1 distance. So you can the interpretation of this after you do some calculation is that the support of the solution cannot be very far away. If the support of the initial condition of the support of this measure of this difference, okay, is very far away from the center, then the V moment is much larger than the M moment. Maybe because one is like the square moment and the other is like it's just the L1 norm. So this tells you that you're not too far. So if you're not too far, you decrease. From this, you can write this. The only change is I added this term here. This is always true because if it's smaller, it's always true because I just added something positive. If this is not true, then you can see that I use the other inequality and I bound this Vn and I will get exactly Mn, and this is always true. Okay? So I just changed this. And now from this is a difference equation with two numbers. I look at the matrix, it's linear, and I calculate the eigenvalues of the matrix. The eigenvalues of the matrix are fine when I have this condition. So this condition is that the constants that you get when you calculate the Lyapunov condition tell you how large the region needs to be so that you can get to the center. Okay, and it's exactly the condition which is written in the other proofs of the theorem. Okay, so we were happy to find this, and this is really it just depends on some semigroup that preserves the mass. It's not really after you do it, it's not very deep. It's very okay. So can we use this? Just say for the Fokker-Planck equation. For the Fokker-Planck equation, it's not very hard, I would say, but you have to use the positivity of the equation. So the hard part is a positivity. For the moments, it's easy. If you do the calculation with the moments, you will see that you get a bound like the one I found. So it's well known that the solutions, if you have solution with a bounded third moment initially for the Fokker-Planck equation, it will have a bounded third moment forever. And you have an easy bound for this. Okay, so this is not difficult. I skip this. What about the lower bound? If I start not very far from 0, so I know the solution is always positive, but it needs to be uniform with respect to the initial condition. One way to do this is to use parabolic Harnack inequalities. This is maybe not elementary, and you have to be careful to obtain some constructive constants. So you need to have some parabolic Harnack inequality where you know the constants. Okay, because from compactness arguments, I may be able I can say, in fact, that if I start with an initial condition on any compact set, let's say the initial condition is a delta on any point of a certain compact set. For each of them, there's a lower bound, and the solution is continuous, so that it must have a positive lower bound, right? So some compactness argument gives you this, but I want an estimate, because if I do this, then maybe I cannot pass the limit in things and so on. So, okay, but you can do it. Still, you have to pass by some positivity result for the equation. I will forget that we have the explicit solution for Fokker-Planck, okay? But if you want to say some more general PD. Then what about the non-local equation? For the Lyapunov condition, it's not a very straightforward calculation, but it's really not top engineering, okay? So it's something that will work with essentially the same arguments that you were using for the other one. What about the lower? This is an interesting one that I want to tell you about. So Harnack inequality, you cannot use it because this equation doesn't regularize at all. So if you start with a delta initial condition, you always have some delta later. The only mixing is coming from the non-local term, which is very regular. So maybe the delta will get smaller, but you don't have a better regularity later. So you don't have this kind of inequality. Then if I fix epsilon, it's easy. The difficulty is to pass to the limit when epsilon goes to 0. So I will give you this idea. So let me do it on the torus. Imagine that I don't have the divergence term, and I want to prove a lower bound for this kind of equation on the torus, even on RD. Okay, on RD, this will not satisfy a Lyapunov equation because it's just some kind of diffusion, so it goes to 0. Okay, doesn't have an equilibrium, finite mass equilibrium, and everything. But I should be able to prove some kind of lower bound. So how do I do this? So this J tells me how far I can jump. So if I jump once, I start at a certain point. If I jump once, I will get some kind of distribution around that point. Okay. If I jump twice, what I get is the convolution of J with itself. If I jump 3 times, it's a third convolution around that. So this, you see, I did this once here. It's Jones formula, and you get just the decay of the initial condition plus something that has to do with the first jump. Now I iterate this, and I will get this. This is actually equal, and this is called maybe the wide representation. It's a relatively common thing in semigroup theory. So you can have this kind of representation, and it's telling me UT, the solution UT is the set of the probabilities of all the possible jumps that the particles are doing. In order to be at a certain point, I can jump 1 time, 2 times, 123 times, and I have to see the probability that for all jumps, I arrive there. Okay? And this is a formula. This is a formula that captures that. So now I need to get a lower bound for this. Okay? So let's do it with the epsilon equation. It's the same, but I use a rescaling epsilon. So now what's happening? I do jumps of size epsilon, but I do them very fast, 1 over epsilon. And then the negative term in the equation, if you remember, it was J convolve U minus U. The negative term has a coefficient 1 over epsilon squared. That's the one I need to write if I write the Duhamel formula. So I get something which is really, really strong. It's e to the minus t over epsilon squared. Okay, this is very small. And I need to show that this sum compensates this as epsilon goes to 0. Okay? So how do we do this? This is the main point of the talk. It's a bit at the end, but the main point. And so it's a link with the central limit theorem. Okay? I have a repeated convolution of many J's. So what's the central limit theorem? This is the usual version. If I have a set of variables which are independent, identically distributed, then I do the right rescaling and they converge to the Gaussian. If I look at the law of x1, xn, let's say J is the law of x1. Then the law of the sum is a convolution. And this over square root of n is this rescaling that I wrote here. Okay? So this is a different version of the central limit theorem. If you have a J, which is reasonable, I mean, it just has to satisfy the conditions that we said at the beginning. It's normalized here. Then if you do repeated convolutions and rescaling, you will converge to the Gaussian. Okay? It's a general principle. So the convergence in the central limit theorem is weak by duality with bounded continuous functions. So, okay, so actually, since I want to get rates, I need rates also in the central limit theorem. So I need to use the Berry-Sen theorem. What does it say? I write it on because it's easier to write and you can see the parallel. And it tells you this. It tells you if you consider the same as before, not only it converges weakly, but it converges weakly with a rate 1 over square root of n. And it depends on the second moment, and the third moment, the variance. Okay, so I get a rate in this kind of convergence. This is a distribution function of S, and this is a distribution function of the Gaussian. So it's the primitive of the Gaussian starting at minus infinity. So this convergence is really the same as weak convergence. So you get a rate here.
Yeah, that's it.
Yes, sorry.
Do you really have this for all?
Yes, I think so. No?
Okay. Because even if you have weak convergence, it could be 7 points where you don't necessarily converge, right?
But this is a distribution function, it's an integral.
Yeah, but I mean, yeah, right.
For all x, yes, okay, this I agree. Okay. It might be so for all continuity points.
Yeah.
That's it, for all continuity points.
Yeah.
And I'm always considering, yes, so the mistake is because I'm always considering f which are regular.
Okay.
But in general, it's at all continuity points. That's right. That's right. Yeah. So okay, there you go. Now what about the same in the PD version? This repeated convolution will converge if I take the primitive. Okay, so this will go to the primitive of the Gaussian at this rate. Now I want to translate this into a convergence of my convolutions of J. This is the translation. I do the change of variables, and I will get this as an easy consequence, right? So the mass of this repeated convolution has to be comparable to the primitive of the Gaussian. Now, this it's essentially the same as this weak convergence I'm talking about. But actually, there are other versions of this theorem. There are old versions by Toscani, which is based on entropy methods, and will give you convergence in several spaces if your initial J is quite regular. There's another one by Goudon, and Toscani, where they do it assuming that you have also some regularity on the J, on the law of the process. You will get convergence also in very strong norms. I'm mainly interested in an L infinity norm. So there are several ways to do this. I can use this paper, or I can set some other condition. For example, if I decide that J has to be radially decreasing, then the integral is bounded by the worst value. Okay, so I can still get some kind of L infinity convergence. So if I have some conditions on J, I can improve this to a better inequality. So what's a better inequality? It will look like this. Let's do it for epsilon. This is before it's in general. Now, for epsilon, I get this. This is what J is satisfying. This shouldn't be RD. It should all be R. Okay, I copied from before, but it should all be R because the example is on. So now this is epsilon squared and this is epsilon cubed. I write the same as before. They disappear and I get 1 over square root of n, and I get this. I use either the results by Goudon, Juncan, Toscani, or some further conditions on J, and I will get some L infinity bound. Okay, this L infinity bound, it tells me the following: epsilon square root of n is of order 1. I have a good lower bound, and this is very reasonable because you can think of this non-local equation as a random walk. So how many jumps do you have to go to get to a distance r? I have to go to a distance in terms of the jump. I have to go r over epsilon. Okay, to get to a distance r over epsilon, I need that squared number of jumps because the mean position of the Brownian motion or of the heat equation, it scales like a square root of time. Okay, so it's very reasonable that this is the good scaling. So I have this. If I just look at n which are of the right order, this is a constant. Okay, this is small. This is the one quantifying the convergence. So if n is large, this is going to be small. If I make this uniformly positive, then this is fine, uniformly positive. So this is what I will use. I use this. I take this condition. This is the expression that I had for the wild sum. Now this one, if I am in a bounded set and I look at an initial, I take my initial condition in a bounded set, and I look at the solution in a bounded set, the sum of them is smaller than r. So I am in the previous condition. So now all of these are bounded by a constant for the good n, not for all n, but the n which are the right number of jumps is bounded below by a constant. Okay. So what do you get? Here I just remove this and I wrote the good summation. Now this thing, it's a sum that has to do with special functions, but there's a rough argument that tells you this is bounded below by a constant. What is this rough argument? So the first thing is, you see this formula is consistent in the sense that if I integrate and I get 1 here, this sum is exactly that. It's exactly 1 over that. So you will get 1. Okay. Now we sum only part of it, but I know that the total sum is fine. So the question is, are the largest terms of this sum on this range? Okay, this is what I need to answer. So where are the largest terms? N factorial, it's n to the n divided by square root of n, right? It's essentially the Stealing approximation that we have. So this is square root of n times, right? It's times. It's square root of n, so it has to fix. It has to go. So it's square root of n times n to the n. So n to the n is like this one here, because you see I'm choosing n which is comparable to this. The only term that I have left is 1 over square root of n. But how many terms am I summing? I'm summing from n equals to this to this. So it's exactly the number of terms that I need to cancel the square root of n. Okay. So this is the formal argument, but then you can do it because this converges to a kind of a special function. There are several ways to do it, but this is uniformly positive. Okay, so it gives you the lower bound, and so the result we get in the end will be, let's say, it's known before, but this positivity, I don't think it's easy to show in the limit as epsilon goes to 0 by any other method, not Fourier. So we get this lower bound. Okay, I use this thing, I will get lower bound. Now, the difficulty is that I still have the problem with the divergence. So there's a modification you can do. Now you do the same kind of wild sum formula. But now it's not only the decay, I have to use the solution to this, and it's interspersed with the other part, right? So there's an iteration of the Duhamel formula where you get convolution, transport, convolution, transport, convolution, transport. Okay. If you change, you can exchange convolution and transport, and you will get something like this. So this means J is scaled more or less depending on the time, and I have a whole integration on all of these times. But still, it looks like a convolution. So what do I use? I use some variance theorem, which is fine for non-identically distributed variables because they are not too far from each other. Okay, they are J epsilon, except for a little bit of a stretch e to the t1, e to the t2, e to the t3. Okay, so I still can use this theorem, and it becomes a bit technical, but the constants work all the same. So you get this kind of final result. This is the final thing I will tell you. I have proved the Lyapunov condition and the lower bound. So I get this. Okay, this is true with constants here, which depend on the argument I have just done, but they are independent of epsilon and they are independent of the initial condition, right? And this result was already, I have to say, essentially this result was already proved by Michel Sani in this 2017 paper. But okay, so it's a new method, and this is essentially what I wanted to tell you. I don't want to go over the time. So thank you for listening.
Y a-t-il des questions?
Do you know of any framework where this method can be pronged to nonlinear program because it is fixed time?
Yeah, not really. Really, this is a common question, I have to say, but I don't know. I mean, the natural thing is perturbative settings, right? But maybe you're not talking about perturbative settings. So if you know something about the linearization, then you can say something about the weakly nonlinear. This is quite common, I would say. But purely nonlinear, I don't know.
Yeah.
So this eigenmode, which you know is specific for couplings, is there any way you could compute the branch out of it for smooth epsilon?
The branch,
Get,
you mean?
get the optimal rate? Because you have a uniform
Yes.
on the rate.
I believe
It's not the optimal.
I believe not with this method. I don't think.
No, but I was assuming this method you would use for the next eigenmode.
Yes,
There's something not optimal for the next one, but study the branch for the one that you know explicitly in the digits.
So the first one is one for both. I mean, it's fixed.
There's
or
the
zero.
kernel, which is
There's a kernel. There's a kernel. There's the next one.
And the next one.
This is estimating the spectral gap.
Yeah, from below. I mean,
That's it. Yes.
But you know it explicitly for the limit equation.
Yes.
You will try to perturb this.
Could be. Yes. I don't know. Could be.
And
To say that the eigenvalue has to converge, right?
yeah, it's an implicit function theorem.
Yes, an implicit function theorem.
theorem.
Yes. A bit of a singular implicit function theorem, but they should work. Yes. I mean, it's probably true. So so something similar to this is numerical simulation for proper Planck schemes, and the eigenvalue converges numerically always. Okay, so it should be true. Numerically, it's clear.
So, thank you for the very nice talk. I have 2 questions. The first one, so you mentioned you consider a non-local approximation to the Planck equation. And you said that the interesting aspect of this equation is that this non-local operator doesn't have a singularity, more or less.
Yes.
Right? So now my question is the natural one is, I guess, is if you were to take one with the singularity, which would be the
Yes.
fractional, is there a reason as to why you wouldn't want to study that equation instead?
Well, no, it's also interesting.
Yeah.
It is also interesting.
Yeah.
Yes. And then the entropy inequalities,
Yes.
they are kind of fractional Poincare inequalities, and they are interesting.
Yeah.
Okay, and they've been studied by in some particular cases they are studied. Then in this paper by Michel and Tristani, they also do the limit from fractional diffusion to classical diffusion.
Yes.
And it's also interesting. It is. So one question would be, if you have some kind of singular operator J, can you still do this kind of thing? And this is not known, I think. So the problems I described are fine if instead of J, you have something more singular. Like for the Boltzmann equation, if it's more singular, like non-cutoff or something, it's hard to do. It's also a question.
Yeah, and just quickly, if I guess you have this toy case with the proper type, but if you have a non-linearity, do you think you could implement something like Butcher series?
Something like?
B series or Butcher series?
I don't know what this is.
You don't? Okay. Maybe we can talk about that.
Okay. So for nonlinear problems, the Harris theorem will not work, or I don't know how to make it work. The lower bound might. Okay, the lower bound might, yes. But
On can du ML.
non, quand tu as, ouais. peut-être.
Y a-t-il des questions à distance? Merci encore.